Hello everyone, this is Eve from University of Connecticut, and I'm very honored to be here to show this video for you. So the topic I want to present here today is about the high temperature energy storage dielectric materials. And what we proposed is by utilizing the 2D MMT nanosheets and coating them on the high temperature polymer dielectrics to reduce their conduction loss and improve their energy storage performance. So here I showed a brief background of the environmental problems, and what we know is that we are running out of the fossil fuels, and that's why we need to find the new energy sources and use some more clean and renewable energies. So the electric vehicle is a very classic example and that we can use and show here. So in this electric vehicles, we can find there's a very important systems. It's called the DC converter. And this is a power system that can convert the energies from the batteries to power the motor. And the reason why we use this capacitors is that we know the battery has a very high energy density, but its power density is pretty low. So that's why we just use the batteries to store the electric energy in the electric cars. But we need some capacitors, dielectric capacitors, to convert the energy from the batteries to the motor because it has a much higher power density. And the materials we normally used in this capacitor is polymer films. So we always adopted some processing method like extrusion or film casting to make a large scale of polymer films. And we wrap these polymer films with the electrode together and construct this film capacitors. But there are some great challenges for these polymer films. The first one is we know that the polymer is more sensitive to the environment, to the temperatures and also the applied electric field when compared with some inorganic materials. So here shows the conduction versus electric field in a high temperature polymer. And we can find with increasing the electric field, we will get the conduction increasing. And also if we increase the environmental temperatures, we can also find the conductions increase dramatically. And this kind of increased conductions can do harm to the properties of the films. Like it can reduce the dielectric breakdown strength, it can reduce the efficiency, reduce the energy density, and it can also do harm to the service life of these devices. And here we presented a new method to improve the energy storage performance of polymer dielectrics. So here we utilized 2D materials, it's 2D MMT, which we used it to coat it on the surface of polyimide imide. And the polyimide imide is a high temperature polymers, which has a high glass transition temperature higher than 300 degrees C. And from the structures, we find that this 2D MMT has a layered structure, and it has a unique properties, which is anisotropic property. So if we check this, the band gaps along this Z direction, we can find it has a very large band gaps, and it makes the MMT is a very good insulator if we just utilize the Z direction property. But if we check the conductivity along the surface, we can find it has a relatively higher surface conductivity when compared with the Z direction. So this kind of unique anisotropic properties is very useful if we utilize this kind of 2D materials to do the surface coatings, and its functions I will introduce later. So from the Dloop measurement, we can extract the discharge energy density, the energy loss, and we can calculate the charge discharge efficiency by this equation. So at first we checked that the MMT content, the influence of MMT content on the dielectric energy storage performance. So we can gradually increasing the MMT content in the coating layer, because in the coating layer we also use some PVB as the binders to combine all these nanosheets together. So if we just introduce 20% of MMT in the coating layer, we can find there are some voids locating on the surface. And if we increase the MMT content a little bit, we can find the surface becomes more smooth. But if we further improve the MMT content, we can find the surface roughness increases. So we will find a rough surface instead of smooth surface. And after we check the efficiency of this coated polymers with different MMT content in the coating layer, we can also find it agrees well with the morphology. So the samples with 40% MMT shows the highest charge-discharge efficiency. And we also checked the influence of coating thickness on the dielectric performance. And we gradually increased the coating thickness from 200 to 400 to 800. And we find there is an optimized thickness, which is 400. And this sample shows the highest efficiency. And we compared this energy storage performance of these materials with this coated PAI with some state-of-art high-temperature polymers. And we can find that our materials shows the highest discharge energy density at 150 degrees C at the same electric field. And we can also extract the energy density at the efficiency higher than 80%. And we can also see that this MMT coated polymer, the PAI, shows outperforming performance when compared with this high temperature polymers. So we did some Finter element simulations to try to find what's the reason that why this kind of coated polymers can have enhanced energy storage performance. So the first thing we simulate is we want to see the current density inside of this coated polymers. And because the MMT has anisotropic conductivity and it has a relatively higher conductivity, surface conductivity, so we can find that this current going to be regulated from the Z direction to the in-plane direction. So it means that this kind of MMT coatings can regulate the injected charges dissipating along the in-plane direction. And we checked the ratio of in-plane current density to the Z direction current. And we find that these ratios can indicate how much current can be regulated to the in-plane direction. And we find that this samples with 40% MMT on in the coating layer shows the highest value, which means that maybe this optimized MMT content can give rise to the highest regulating effect of this coating layers. And we also checked this ratio in the coated polymers with different coating thickness. We can find that if we increase the coating thickness, these values can be gradually enhanced, which means that maybe we need a thicker coating layers to get a better performance. So this figure shows the mechanisms, the schematic illustration of this coatings. So if we got some charges which are gonna injected from the electrodes, so some of them will be blocked at on the surface because we have MMT coating has a large band gap, and there are also some charges could be regulated that are regulated dissipating along this in-plane direction because this MMT has a relatively higher surface conductivity. And there are only few charges can finally go through these interfaces, and this part of charges can contribute to the final conduction loss. So in addition to the current density, we also need to pay attention to the electric field strength, especially inside of these coatings, because there is a contrast of dielectric constant and the conductivity between this MMT and this polymer binder, and also the polymer matrix. So we'll get some localized region has relatively higher electric field. And we see that if we just increase the MMT content, the maximum electric field in the coating layer does not change too much. But if we check this coated polymers with different coating thickness, we can find that this samples has a very, very high maximum electric field inside of this coating layer. And one possible reason is that when the coating layers become thicker, the MMT nanosheet is going to be tilted a little bit, and this tilted MMT nanosheet is going to touch with each other much easier, and it can finally result in some enhancement of the electric field in some localized region. So, so previously we mentioned that this samples has the highest value of the GXY, the ratio of GXY to the GZ, but now it has a very high electric field inside of this coating layer, and this becomes a drawback of this thicker coating. And we also simulate the temperature of the samples with different coatings, and we can find the first thing we find is that all of these coated samples has a lower temperature when compared with pristine PEI. So the environmental temperature we keep the same is 150 degrees C, and after we applied the electric field, and because of the true heating effect, all of these polymers will have an increase of temperature. But with these coatings, it can reduce this kind of improvement of this increase of temperature. And there's one thing we need to notice is that we didn't consider the voids inside of this these samples with 20% MMT, and we also did not consider the surface roughness of this sample with 60% MMT. So we may underestimate the temperature rising in both of those two samples. But if we compare these samples with different coating layers, we can find that if we just have 200 nanometer coatings, the temperature is pretty high. And if we gradually increase the coating layer to 4 layers, whose thickness is 400 nanometer, and its temperature gonna drops about 10 degrees C. But if we further increase the coating layer thickness, we can find that the temperature rises again. So it agrees well with the analysis of electric field distribution, what we mentioned in the last slide. So here I will give a brief summary of this work. So firstly, we designed and manufactured high temperature polymers with this 2D MMT nanocoatings. And we proved that this kind of coated polymers will show reduced conduction loss and enhanced charge discharge efficiency. And from the Finter element simulations, we disclosed that these MMT coatings with anisotropic conductivity can show a very significant influence on the current density distribution, electric field distribution, and also the temperature rising. And that's all for my presentation, and thanks for all the group members from my group, and thanks for your attention.